proportional to k mu k rho. And we saw how in the last course to show that they cancel, yes, by using the Dirac equation in the one loop present. Okay? So the replacement of this object, where in fact the gauge dependent terms cancel, as we showed, is simply becomes minus j mu pi 1 normalized k squared divided by k squared pi 2 normalized k squared. Okay, so it's very simple. Note that there is a difference with the two-loop result, because with the two-loop result we have the replacement of basically this. Here we all replaced by, no, it was exactly this, no one here, and there was a plus sign. There was a plus sign. Okay, but it will be cancelled when we will put, in fact, you remember how we yes, when we will use the dispersion relations, will cancel. Okay. So we do the same as before. We use dispersive representation of the two here, and we inject it in the one loop present. Okay? Because, well, we'll see now. We'll find minus I yes S 0. Okay, this is the first dispersive integral. Imaginary part of 1 R S 0 infinity dt you have 2. Okay, so 2 dispersive things. By t. Okay, and now you have the integral over a for k divided by 2 pi power k. The usual thing. Okay. Okay, there is gamma mu, and this time we have the k square, but here there are some k square in the numerator, so the only thing that stays is this 1 over s minus k square times k square over t minus k square. So it's a bit more complicated, but there is a trick to do such things such that you will become at the end with the one loop result, with a massive photon. Okay? Otherwise here it's not anymore a one loop result. Okay, you see it. Okay, there is one propagator, and this we see that very much here at least looks like. So the trick is the following. What you do is to express this object as minus s 1 over k square minus t minus s over t minus s 1 over k square minus s. Okay? Then we will have two integrals that with your massive photon propagator in each. Okay? So if you insert this here, you compute the corresponding integral, you find that anomaly contribution of this diagram is simply equal to alpha of pi integral 0 to infinity ds divided by s 1 over pi and part of pi 1 over s 0 plus infinity dt over t times 1 over s 1 over t minus s. Okay, this is this one here. Well, there is a simplification. This times 1 over 5 imaginary part of 5 over t times your famous Schwinger integral multiplied by t minus s, that we cancel this one, times x squared divided by x squared plus t over x squared times 1 minus x times the same thing is t replaced by s. So it's very symmetrical, very nice and simple formula. S over m squared times 1 minus x, and that's it. Okay, so we therefore may use once more dispersion relation to obtain AL equal alpha of pi integral over x to the power of 4. No, that is to the power of 4. 1 minus x pi to the power minus x over 1 minus x times pi minus x with the same mass. Yeah. Okay. Because the dependence on the mass of the internal fermions are not in this part of the function, but in the rest of the function. Not in the parameter. So this is a simple, very simple and very nice formula. You see that the trivial calculation in this case, perhaps you can do it, but even in this simple case, it's not easy at all. And this is the last diagram in QED that has been completed at the trivial level, which means that, well, that's why to say that to the anomaly, the contributions are very, very small, so it was ignored for a long time, but it's also perhaps because it was depending on two
ratios of masses, and this is the first in the perturbative series, okay, to depend on two ratios, because at two loops there are no, you remember, we computed them, no mass-dependent contributions that depend on two ratios of mass. So, okay, so it is more complicated to compute, but it is anyway a simple diagram compared to the others. The others you cannot try to compute them here. If you always it's impossible. It took 30 years to remedy and collaborators and a lot of other people to compute the theory level. Okay, 30 years. Only the contribution to the anomaly. These are exact calculations, exact analytical calculations. So you know by heart that this may be expressed as an integral of a logarithm. Remember? Okay. This one also. You put these integrals here, and you use the daily bounds of the rotation of the log that I showed you, log of 1 plus x equal integral over c minus etc. 1 over s gamma de, well, pi over sine pi s, okay? And then at the end, since I'm close to time, you will be able to replace the k-square determinant square. It has been replaced already, but you will have an S determinants of these objects here. You will find some beta functions as we did. And these beta functions will induce some constraints for the integral to converge, but we will fulfill this constraint. You will be able to perform the replacement by the gamma functions. And at the end, what you will get is the following. L equal to 4 alpha over pi q squared c minus s d minus s, okay, n squared over n1 squared power minus sigma n squared over n2 squared minus t times 1 over sigma 1 over 2 gamma squared 2 minus sigma gamma squared minus tau divided by gamma 4 minus s gamma 4 minus 2 pi over sine pi s pi over sine pi tau times gamma 1 minus 2 sigma minus 2 tau gamma 2 plus sigma plus tau divided by gamma 3 minus sigma minus tau with the conditions minus 1 is Also. Okay? So this is the same method with Raphael and Grenard. Is that and since time is off, next time we will see how to manage with this kind of double volume bound integral.
Thank you. So, you don't mind if you lecture last time on Tuesday? Maybe so Tuesday at 2 o'clock, or you prefer on Monday at 2 o'clock?
I prefer Tuesday because I have to prepare it.
Good. So, last lecture, na última aula, terça-feira de 8 horas, tá bom? Aí vai falar um pouquinho também sobre o momento de bola elétrica. Ok, Sam, thank you so much indeed.
Merci.